I was muted. All right.
So we're very happy to have Peter Smillie from Caltech, and he will be speaking about the border of outer space. Thank you.
Okay, I just lost my cable connection. Oh, and it's finicky. Sorry, this just happened now. I'm going to try to get another cable. If not, I'll switch to AirPlay. Let's see if this one works better. Let me try to reconnect without a cable here. Sorry about that.
Another option is to make your tablet, to connect your tablet to Zoom directly, right?
Yes.
Just in case. Yeah.
Screen mirroring. Oops, that's not the right thing to press. Okay. So this is working. Okay, so I don't think I put this in the abstract. This is all joint work with Kayuba Books and Karen Goldman. And they're talking about the border of outer space. So the topic here is virtual duality groups. So here, gamma, in the context of discrete infinite groups. And we say gamma is a virtual duality group if every torsion-free finite index subgroup gamma prime is a duality group, meaning there is a gamma prime module d, an integer, a dimension d bigger than 0, so that this form of Poincare duality holds. Cohomology of gamma prime with coefficients in any module is the homology h d minus I of gamma prime with coefficients in d tensor m. So here, this d is called the dualizing module. Little d is the dimension. This tensor product here is gamma x diagonally. And of course, the canonical example is if gamma is pi1 of a closed manifold. In which case,
hey,
by Poincare duality, yeah?
Sorry, you should have finished your sentence, but I wanted to quickly ask whether this implies anything about gamma with rational coefficients then?
I don't know of a statement like that. Other people might.
Okay, thanks.
Yeah, sorry. Okay, so the canonical example here, gamma is a duality group if gamma is pi1 of a closed manifold, in which case this holds, with D being the orientation sheaf of M. Okay, so now, okay, from now on, I'm going to strengthen the assumption a little bit. Not just a discrete infinite group, but I want to talk about discrete infinite groups which act properly on a simplicial complex, a contractible simplicial complex with finite quotient. And really, the assumption I want to make here, for those of you who know what this means, is I want to make sure gamma is FP. This is a little bit stronger, that's fine. So if gamma is acting properly, then gamma prime, any torsion-free finite index subgroup, would always be acting freely, still with finite quotient. So here, if gamma prime is a torsion-free finite index subgroup. Okay, so under this assumption, there's a theorem of Berry and Ekman, who I guess also defined the notion of virtual duality group, which, what they do is they identify the module D. Specifically, gamma prime is a duality group, if and only if there exists a D such that the module, the complex, the cohomology of gamma is coefficients in the group ring, is supported only in one dimension D and is torsion free in that dimension. By the way, this, I didn't say before, but this dimension D, and in some sense the module D, don't depend on the choice of gamma prime. So canonically associated with gamma. Maybe I should put a gamma prime in here. I'm probably going to miss a lot of primes. So, and in this case, this lone dimension, which this is non-zero, you get the dualizing module. So just to point out, this is a gamma prime module. It's a right gamma prime module via gamma prime action on Z gamma prime. Okay, so what do we like about, well, what's geometric group theory all about? So the assumption here that we're acting on a simplicial complex means that you get a free resolution of Z as a Z gamma prime module using the simplicial K-chains on X. Specifically, because the quotient is finite, you actually get a finite resolution, finite length, each one is finitely generated. So we can compute, under this assumption of the action, we can compute the dualizing module using this resolution, right? So you take the Hom of this chain complex of X to Z gamma, take the cohomology of that complex, and you've got the cohomology of gamma with coefficients in Z gamma. And here is kind of the trick, which means I don't have to keep talking about this Berry-Ekman stuff in the future. The trick is that you can replace the group cohomology with just the compactly supported cohomology of the space X on which gamma acts, putting it on firmer ground. So what's going on there? So this is just for each, where we have this complex, of cochains, and at the level of each term in the complex, we just have the isomorphism that Hom gamma CK, or Hom gamma of anything Z gamma, is the same as the C stands for, well, it's geometric, so it's straightforward, it's just compactly supported. Changes values in Z. And the map here, if you have a gamma homomorphism from the chains, right? So of course gamma is acting on the chains in X because gamma acts on X. This is can be expanded as a series like this, where these are all, this is a finite sum by the nature of the group ring. And saying that it's a gamma homomorphism is exactly this relationship between the coefficients, little f gamma. So if we, so in particular, F1 determines all of the little f gamma. And so if we just forget about all of the coefficients except for F1, we get a map from CK to Z, and it's compactly supported because the sum is finite. Well, because the sum is finite, and so all but finitely many terms of this are non-zero. So for all but finitely many of the chains in the orbit of gamma, well, yeah. So let me stop there. Okay, so the corollary is that the cohomology of gamma with coefficients in Z gamma, this dualizing module is just the compactly supported cohomology of X with coefficients in Z. So in sum, the point is that if we want to show that gamma is a virtual duality group, we need to give a proper cofinite action of gamma on well, it turns out it's okay to assume it's a simplicial complex, and just show that the cohomology of this complex has this form. And the thing I want to point out here is having done this, we really kind of have very little about gamma left to show. Like, once you have an action of gamma, which is proper and co-compact or cofinite, now you forget about gamma, and now you just want to prove this property of the space X. Okay, so this general scheme has been used several times to prove that groups are virtual duality groups. The I guess first example is if gamma is a arithmetic group, or more generally an S-arithmetic group, meaning you can invert some primes. So for example, GLNZ. In this case, Borel and Serre used this construction to prove that gamma is a virtual duality group. Next, the mapping class group of a surface of genus G with S punctures is also proved by Hare and Ivanov this way to be a virtual duality group. Oops, GS. And then finally, the example in this talk, so out of Fn, the outer automorphism group of a free group was proved, and this is in 2000, by Bestvina and Feighn to be a virtual duality group by constructing the space X and showing that the cohomology is supported in dimension D and freeing that dimension. Okay, so I say they constructed a space X, but actually you'll maybe see that in all three cases, we kind of almost have an X already, right? So we already have a natural proper actions of gamma on some space, some simplicial complex.
Can you scroll up a little bit?
Yeah. The upshot? Or I can scroll up further.
Oh, I only see example mapping class group on the very bottom. I don't know if that's just me.
Yeah, no, perhaps this is paused. That's the danger of connecting by internet. Let me try pausing and resuming. Oh, that works. Okay, sorry, was there something specific you wanted to see now that I've scrolling capabilities?
No, or scroll down, I meant, not up, I guess.
Down, yes. So that's,
because you were talking about things that weren't visible yet. Thanks.
Yeah, so thank you. That was the connection's fault. Please continue to interrupt me when that happens. Might take them. Okay, so in all three cases, we already have natural proper actions, which we could make simplicial. Namely, I'll just restrict to the example GLNZ as a representative arithmetic group, S arithmetic group. We have an action on the symmetric space of SLNR mod SON, the space of positive definite inner products on Rn, which is proper. We have, in the case of the mapping class group, Teichmuller space, the space of conformal structures on a surface. Marked, put this, marked with the homotopy equivalence to a fixed reference surface, so that the mapping class group with that fixed reference surface acts on it. And in the case of the outer automorphisms of a free group out of Fn, we have, thanks to the construction of Color and Botman in '86, outer space. So outer space, I will draw more carefully in a minute, but this is the analog of Teichmuller space here. It's marked metrics on graphs of genus N, with N, with H1 rank N. And you're marked by a homotopy equivalence from a fixed graph of genus N. Okay, so what's wrong with these actions, though, is that the quotient in no example is compact. Well, not compact. So we're not going to be able to apply Beer-Ekman in these cases.
Can I ask you a question?
Yeah.
So is there like non-positive metric or some sort of hyperbolicity property on outer space?
Yes, there are hyperbolicity properties.
Okay.
I would be worried I would say something false if I tell you exactly what they are.
Okay, sure, thanks.
I'm sorry.
It had zero space, right?
I believe so. Thank you. Okay, so the quotient is not compact. The action is proper. This is good if you take cohomology of these spaces with convex supports. I mean, the first two are homomorphic to balls, so you would get, as you know, just a modulo supported in degree 0. Or never mind. You get there'd be Poincare duality groups, which is not the case. So there are relationships between these three spaces. All right, so a mapping class group, if there are punctures, well, a punctured surface is homotopy equivalent to a wedge of circles, to a graph of genus G. And so in out of Fn, where we're looking at you know, K-pi1s for Fn up to homotopy equivalence, this gives you an inclusion of the mapping class group into out of Fn. And then by looking at the action on H1 of the graph, you get a surjection from out of Fn into GL and Z. These maps are compatible with the actions on these spaces, so there are also relationships between these three spaces. And in a special case, these are all isomorphic, and that is conveniently the space in which you can draw pictures. So let me draw that picture. Okay. So if n equals 2 out of Fn, you have these isomorphisms. Mapping class group of surface of genus 1 with 1 puncture is the same as out of F2, is the same as GL2Z, and these all act on the hyperbolic plane. The quotient being, well, the modular curve, except I have an extra involution here, so kind of half a modular curve. And this, as you see, is not compact, as I warned. But one thing you could try to do is just add on something to compactify it. A natural choice would seem to be a point at infinity. In which case you do. So this corresponds to adding the gluing on all of the rational points onto the boundary of the hyperbolic plane. And now you do get a co-compact action, but the stabilizer of this point is the unipotent group, so the action is no longer proper. Easy fix. Instead of adding a point for each point of Q, you add a line at each point of Q, which you can think of as performing a real blow up at each point of Q, looking at all directions into that point. Okay, then the quotient is compact because now the stabilizer is acting the translations on that line. So the quotient is specifically the modular curve plus a circle at infinity. Quotient is compact and the action is now proper. So now we've satisfied both conditions. We call this space H bar. That's H union lines at each rational point. And let's do a little basic computation to check that this is a virtual duality group. Right, so HK with compact support of the hyperbolic plane, or sorry, of H bar. So the point here is that I'm using Poincare-Lefschetz duality. In this first step to replace that with homology. But it's a little bit tricky because this precise version of Poincare-Lefschetz duality is not in Hatcher. I'm using it for the non-compact manifold H bar. And so, but that's okay. It's still true for non-compact manifolds. But it's a non-compact manifold with boundary. Right? So you have all these extra boundary components added on. You know, if you approach the boundary components, well, it's compact in those directions. Okay, and so I'll draw a picture of this in a second. So the first equality then is true, and then the second equality, I guess we need a reduced homology here. This is for, this is just the long exact sequence of the pair. And here this is just countably many contractible components, and so the result is if k equals 1, you get countably many copies of z, and if k equals anything else, you get 0. And so this indeed satisfies Beery-Ekman's condition to be a virtual duality group. And so this shows that any of these three equal groups is a oops, I have the right Poincare there, is a virtual duality group of dimension 1. You know, note that this module, importantly, is not just Z, it's some infinite rank module. If it was Z, you call it a Poincare duality group. It's not a Poincare duality group, but it is a virtual duality group. Cool. So just I don't want to linger too long on the Borel-Serre case, but just to point out how the numbers work. For GLNZ, there's an analogous bordification, meaning I've added some pieces of the boundary, but not completely compactified the symmetric space. You glue a Euclidean space for each flag in Q to the n, and the a theorem of Solomon-Tietz shows that this the boundary, the stuff you glue on, has the homotopy type of a wedge of Sn-2s, of n-2 spheres. So just going through the same computation here using Poincare duality, and then the long exact sequence. So the symmetric space has this large dimension, you know, n times n plus 1 over 2 minus 1. The boundary has dimension 1 smaller. The wedge of spheres, the reduced homology, is supported in dimension n minus 2. So you do some algebra, and you get the GLNZ is a Poincare duality group of dimension n times n minus 1 over 2. There's a virtual duality group of dimension n times n minus 1 over 2. Okay. now we have a better way to draw pictures. So, and confers some other advantages too, as we'll see in a second. So you can do the same construction, but instead of adding a circle off at infinity, let's just cut off the cusp of the modular curve. So it's clearly homeomorphic, but now we can draw this picture a little bit better. So here below is a picture of the hyperbolic plane. And I've just removed these horiballs. And now this is tiled. Kind of stop drawing tiles because that's gonna not go well. And what did I say? So you recover the same picture in now a much more drawable way. And this, I guess Grayson showed that this works more generally for GLNZ and Sapir. Applied this to SP2NZ. So that it showed that you recover I guess recover the symmetric space, the Borel-Serre bordification of the symmetric space. Right. So just going back to the compactly supported cohomology, maybe this is not confusing to other people, but right. So applying Poincare duality to this hyperbolic plane with these horiballs removed, right? Of course, compact support, the boundary of the horiball is still in the space, and so it's Poincare duality. Poincare-Leschetz duality says that the cohomology with compact support of this space is related to the homology of these unions of horospheres. Okay, so that's the introduction, and now let's talk about the case of outer space. So for out of Fn, as I said, Bestvina and Feighn defined a bordification, xn bar, and prove the result you need. The cohomology with compact support of xn bar is of the form you need, and the action of out of Fn is proper and co-compact, co-finite. And so we just perform the analog of Grayson's translation. So we define a equivariant deformation retract, which we call the Joule complex, Jn. We prove that Jn is the same as the Bestvina-Feighn bordification by just writing down a homeomorphism. And we then give a new proof that, besides Bestvina-Feign's proof, that this space is 2n minus 5 connected at infinity, meaning that okay. I've applied a boundary map there in that statement. New proof of Bestvina-Feign's result. Just wanted to point out that this is sufficient. So we only need to worry about the showing the lower cohomology groups vanish, because we already have an action on a 2n minus 4 dimensional space, dimensional complex, called the spine of outer space. and so if you have an action on 2n minus 4 dimensional complex and it's 2n minus 5 connected, then it follows that the cohomology is supported in dimension 2n minus 4 and is torsion free. And then finally, we give an analog of the Tietz description of the boundary of the dual complex. So it's covered by contractible walls, the analogs of these Euclidean spaces, and we give a description of the intersection complex, but not quite a good enough description yet to see if it is a wedge of spheres. So you could ask, is the boundary of Jn homotopy equivalent to a wedge of S 2n minus 4s? You could ask this, but let me also warn that this case is a little bit different than the other two cases in that you're not acting, the outer space is not a manifold. And so we can't use the Poincare duality isomorphism to describe the boundary. So the relevance of this question to the theorem, well, it's to be seen. Okay, so let me now just going to look to these points further after giving a definition of outer space.
So what are the main obstacles to like finding a nice simplicial complex that's spherical whose top homology is the dualizing module, similar to like the top homology that Tietz building is the dualizing module?
The main, well, I mean, you need a construction.
Yeah, or I guess like which parts of what you're doing is like different than what like Borel-Serre or the mapping class group case.
So I think what we're doing is very analogous to what Grayson is doing. I mean, Bestvina-Feighn really have the analog to Borel-Serre. You have to find what are the analogs of flags. What do you have at infinity? Yeah, I mean, it's so in our case, we need to show that when you, I guess maybe here's what I would say. No, I'm not sure.
We can talk more after the talk.
Yeah, maybe we should talk more after. So yeah, let me define the dual complex. Maybe an answer will become apparent. So the space Xn, before we bordify it, is, as I say, the space of metric graphs. So I want metric graphs G of genus N. They're going to be finite connected metric graphs, and so I could ask that they have total length 1, or equivalently look at them up to rescaling. I want to make sure, so for instance, G could be this, if n equals 3. And I want all vertices valence at least 3. I want no separating edges. So what's bad? An edge that if you remove, the graph becomes disconnected. Just this is also, I want to count this as a separating edge. If you had just a single edge going out there, that's sort of both eliminated by the valence condition, but I also think of it as a separating edge. And marked by homotopy equivalence from the rows, fixed rows Rn to G. Okay, so here's a picture of outer space for n equals to 2. So the relevant graphs are just of two forms, right? The only, oh my goodness. The only graphs satisfying these conditions are the rows or the theta or sideways theta graph. And so here we see that outer space is a union of open simplices corresponding to the type of graph. Right? Each simplex is just the projectivization of the positive orthant in R to the k, where k can depend on the graph. It's the number of edges. And what happens, how are these simplices glued together? Well, here's a picture, I'll zoom in. If you contract this middle edge of the theta graph, then you're moving to one side of the simplex. Let's say you're moving to this side. And now this rose has a new automorphism that the theta didn't have, where you can flip one of the two edges of it, and then you can expand again. And when you do that, one way to keep track of what's happened is now the marking is different, right? Now this purple map is supposed to be the map from the rows. You've flipped the direction of one of the loops. And just to see what happens if you keep going, well, it's can be more complicated, right? If you, instead of this way, if you contract the left edge and thereby approach this boundary component over here, so here's the center. Now you see your marking has really got all twisted up. So if you flip it and expand more in this direction, you'll get kind of a whole new marking of your theta. Yeah. Okay, so that's a picture of X2. As I say, it's a union of open simplices. And let me look at one of these simplices a bit closer. So actually, everything I'm going to say is marking invariant. So let me just write sigma of G for the closed simplex corresponding to the graph G. Marking is irrelevant. Okay, so I'm describing how to start with this outer space and give a subspace, which is the Joule complex, which is supposed to be co-compact. Right? You have these non-co-compactness issues at the vertices. Okay, so the faces correspond to proper subgraphs. The way I want to think of the correspondence is the face corresponding to a subgraph H is where the length of all the edges in H are 0. So if you set the length of all the edges in a subgraph to 0, you get G with H contracted. Write that G mod H. This is a face. But this is these are supposed to be the closed simplex. And not every face of the closed simplex is actually part of outer space. The problem is if you contract a graph, you could change contract a subgraph, you could change the genus. And so the face corresponding to H is in outer space still, if and only if the genus stays the same when you contract it, which turns out to be the same as saying that H is a forest, has union of trees inside G. And I want to just rephrase this in a third way. It's also the same as saying the core of H is the empty set. So this core is a concept I'm going to define right now. We say a subgraph is core if it has no separating edges. That's it. So this guy is core. This guy is not core because if you remove this edge, you separate it into two different vertices. This guy is core. It does not need to be connected, but for obvious reasons, this guy is not core. This is a separating edge. This is a separating edge. Okay, there's a definition in the middle of the sentence. The end of the sentence is the core of H is the largest core subgraph contained in H. So if you contract H, you've contracted every core subgraph of H in particular. And the way you build the dual complex is just by contracting all of the, or is by shaving, rather, outer space at the faces corresponding to all the core subgraphs. In a little bit more detail, we construct the dual complex cell-wise, so it's just an operation on each open simplex. Jn is the union of the jewels corresponding to each graph. Again, I don't care about the marking. And to get the jewel of a graph from the simplex of the graph, you shave the face where, for each core subgraph, you shave the face where that vanishes. Okay, so this is sufficient by this property here to make the action co-compact. Okay, so a picture of this for the theta graph, you have three edges. We label the faces, the codimension one faces, kind of the divisors of this of the simplex by the edges that get contracted. So now for each, so the core subgraphs of this G, we decided were pairs of vertices. And for each one, we want to shave the bit of the simplex corresponding to that core subgraph. So what we're doing here is we're setting up a little barrier. And we're saying, okay, you're not allowed to contract any core subgraph beyond some amount epsilon. So over here, right, this picture looks like E1, E2, E3. Lies over that. On the other hand, if you have a rows, now every subgraph is core. So you have to shave every face. And so this is the jewel of G. Okay, and so these fit together to form a complex Jn. So, for instance, here with this theta graph, I'm going to pull up here. You see we're shaving little piecewise linear horocycles around all these vertices. Okay, and the special case where we have a rose is important. So if you have a rose, then you need to shave every face. You get what's called the permutahedron. It says the property that vertices correspond to orderings of the edges, and faces correspond to non-empty proper subsets of edges. The faces of the permutahedron, J of the rose, vertices of J of R. The containment relationship here is given as an ordering is in a subset, is in the face corresponding to a subset if the smallest n elements, the smallest k elements, smallest size of s elements are exactly s. Okay, here's one more example. for this G, we have various core subgraphs. You have to shave various faces of this. Okay, and so to Jeremy's question, what kind of is the, where do you get hung up here? So in proving that this is highly connected at infinity, a important lemma ends up being, as we'll hopefully see, that so for every joule, the vertices of the joule are exactly those vertices contained in the row's faces. So every vertex lies in a row's face. That means corresponds to a rose and it's a vertex of that. So, and also an ordering of the edges of that rose. Okay, so come back to that in a second.
Sorry, that just means you contract a spanning tree. Is that what you're saying? Or a spanning forest?
Yeah. So a rose is a spanning tree is contracted. So
yeah.
Yeah,
But that's how it shows up, right?
That's how what shows up.
The rows from any given graph. You're saying about
yeah,
the vertices.
those the rose faces are the faces
Yeah.
where you've contracted a spanning tree. Exactly. Okay, and so the first two theorems we prove about this space. Actually, so I think I prefer to switch the order up here a second, just because I've sort of been putting out remarking that you need to choose constants, how much you shave. So the right way to do this in order to guarantee they fit together is to shave by an amount which only depends on the dimension of the face. So you impose some linear inequality. As long as your constants are growing rapidly enough, say if each one is bigger than twice the previous one, the combinatorics of the resulting polyhedron is determined. And okay, here's a little aside that I can't say any more about. Is that Dirk Kreimer is working on so analyzing Feynman integrals in quantum field theory as integrals over outer space. They're non-convergent integrals over outer space, and so what do physicists do when you have a non-convergent integral? Well, you truncate the domain over which you're integrating, and then think of it as a function of the amount you've truncated up by. These are called renormalization parameters. So a posteriori, maybe what we are doing is just describing the renormalization parameters of the Feynman integrals over outer space. But, okay, that's yeah. That's how you choose your constants. Okay, so assuming we've chosen our constants with to be growing quickly enough, we have that. First of all, Jn is an equivariant deformation retract of Xn. And second, it's actually naturally homeomorphic to the Bestvina-Feighn bordification. And as I say, we just prove this by writing down a map, which is not too hard to write down in these coordinates. The map is at the level of cells again, and you just need to check they glue together. I'll just say a quick word about this. So the way Bestvina-Feighn defined their bordified space is by embedding each open simplex into a product over all core graphs of the simplex corresponding to C. So you're just projecting down instead of taking a face, you're taking the projection, the sort of degeneracy map instead of the face map, and then they take the closure of the image in this product. So here's a projection of the simplex down to the E1, E3 face. So we just have to define a map where instead of projecting from the open simplex, we're projecting from the jewel. And as I say, there's a relatively straightforward formula for this. You basically have to decide which facets of the jewel are going to which boundary points of the image over here. And this is the right choice. So you can kind of extend the map this way. And you get a homeomorphism. Okay. But the main content of this paper is that this jewel space is highly connected at infinity. And so let me give an idea of the proof of this. So it's analogous to the original proof that outer space is contractible. And as I say, we have to use our characterization of the jewel as the convex hull of the row spaces. And we use that as follows. So the first step is to replace the jewel complex by a simplicial complex where the vertices are the marked roses. And K-simplices are markings of the rows, which are all contained in the same jewel. So, the jewel complex is not yet a simplicial complex. We're just kind of turning it into a simplicial complex by collapsing these row spaces to points. And so by proposition, this subscripts ln is homotopy equivalent to jn, properly homotopy equivalent. I have the same. Okay, and so now we should compute the cohomology with complex supports of ln, which just means the limit over any exhaustion by compact sets of the relative cohomology, hk of ln minus ki. And to show that it's highly connected at infinity, what that means is that if you have a map from it's sufficient to show that it's highly connected, that this group is highly connected for all, this complex is highly connected for all I, meaning if you have a map from a sphere into ln minus ki, then you can extend that to a map from the disk into ln minus ki. But because ln is contractible, by Kohler-Waltman 86, we know that there's a map from the disk into ln, which extends f. Okay, so to prove that this guy is highly connected at infinity, what we need to be able to do is homotope our map into ln from the disk into a map away from the compact set. And so the idea, the natural idea, is to take the compact sets to be sublevel sets of a Morse function and use the gradient flow of that Morse function to homotope the map of the disk away. But what turns out to work nice is instead of using a continuous differentiable Morse function, to use a more combinatorial argument here. So you have a simplicial Morse function, meaning a function on simplices of this complex ln that is a function on roses. And you just move your map outside of ki one vertex at a time. Right? So you need to show that, right, so for each vertex, you have some link of that vertex, and the link is divided by the Morse function into the upper link and the lower link. And all you need to do is show that the upper link is also highly connected. And this is just a local problem. If you've shown that, then you know that the whole complex is highly connected at infinity. And so that's how you prove that. Yeah, so this is probably a reasonable place to stop.
Okay, let's thank Peter. Are there any questions?
So I'm just curious. So the dual complex already existed, right? And I guess these truncations already existed. Or, I mean, this is a question because I was interested in this because I also talked to the Kramer a lot. So I'm actually also, but you said you don't know much more about the renormalization. So I'm just asking, you know, I mean, I know that these complexes existed and the truncations existed. Is that fair? So, or you know, did you define them in this paper, or somehow it wasn't clear to me that there was a source for that, a written one? It's just an information question.
Yeah, no, I don't know of. I didn't know of them existing before this paper.
Okay, yeah, that's what I thought.
I believe they did, but in any case, we showed, you know, both that this complex
so that's
is homomorphic.
So then that's part of it. Making that strict as part of the results. So that's actually great. Then I was confused about, you said, I mean, something about the rates, but also you don't want to cut in too far. I mean, the whole point is, I mean, if you're thinking about this, you don't want to move in too far either, because then they start overlapping. That's I always thought that was a more exactly more of a problem than actually they're not overlapping. All right, so that's, and that also guarantees that then they don't overlap, right? Because they sort of had if you iterate this, you might have different problems depending on how you look at it. Okay, so that's good. And then did have a last question. Right, so it's clear that, yeah, equivariant you show, but then yeah, okay, I think yeah, the rest I'll have to read. So I mean, I still don't know. Did you describe, maybe I missed it, you said something about this Bestvina complex. Did you say much more about that except for this open embedding into the simplices, which I couldn't visualize very quickly? Yeah,
I didn't say much more, but what you get, that's the point is exactly that it's hard to visualize. So just a comment. So
yeah, but
I mean, it's important. It's important for their theorem that these guys are indeed cells, homomorphic to closed balls, and actually,
no, sort of, yeah.
Their proof of that, they appeal to the Poincare conjecture.
Okay.
Because it's hard to visualize, and ours is easier to visualize.
Right, but I mean, just the thing. So usually these things are given sort of, you know, as blow-ups, like in configuration spaces. You sort of collide two things and you blow them up, right? And I mean, what you're doing is sort of cut off renormalization, so you're cutting them off. So it's like exactly cutting instead of blowing up. And I was wondering, I mean, there are always these things. Of course, they're dual to each other or even the same. This is a serious question. They're dual or the same. So I was wondering if this Bestvina sort of is something like a blowing up procedure. Is like that, like
so this is exactly. That's exactly how you should think of this. As the projecting onto these things is exactly how you is one way to define a real blow up, right? If you want to blow up a point, you embed, say, in the corner of a cell, you embed the cell into the product of itself with the line of directions from that point, right? And then you get this, so that's a third dimension.
Right.
And twisted guy, and you take its closure, and that's the blow. So that's what's going. So we're just doing that every guy at once.
But then being non-algebraic geometry, you don't blow up, you blow up with lines. That's what you're saying, instead of taking something compact, and that's why you get something non-compact.
So I mean, in fact, these are compact. These
they are
guys,
compact. Okay, so you don't take lines, so you do take S1s. Okay,
but
okay.
you don't get circles.
Wait, but the
segments.
LNs are not compact. Like your bordification is not compact. It's just at these.
The whole bordification is not compact. The quotient is compact. So each cell is compact. The quotient by out of Fn is compact. But out of Fn is an infinite group, so the total space is not compact.
Yeah, that's good. All right. Okay. Okay. All right. Yeah. Thanks. That makes a lot of sense. Okay. So basically, you're proving that blowing up and cutting corners is the same thing.
That's yeah.
Okay.
Can I ask a question about this complex you defined Ln, because I didn't quite understand what that meant,
Yeah.
what you wrote there, or it's like can you just explain this point number 1 again, because I just didn't understand what was going on there.
A picture here. So here's a joule. So the the vertices of the joule, right? The proposition is that they're all contained in row spaces.
So I mean, this 3-dimensional, or these 3 simplex, the whole thing corresponds to a rose, right? Or does this correspond to G?
This corresponds to G. Actually,
but then we could contract E2 or E3. We could contract those to get a rose, and so
yes.
Then those the corresponding spaces should not be cut off.
Yes. Yeah. Those correspond to this rose. This is the rose E3, correspond to contracting E3. And I don't know where E2 is, but so the point is to get Ln from this. You replace the rows with just a vertex there. Let's see another one. And then, sorry, here's E3, or E2. And a vertex here, and then you just take the simplicial complex where correspond in J, just where the vertices are these roses, and you connect them with a cell. So in this case, it'll be one-dimensional because there's only 2 roses that you can contract this graph to.
Okay, I see. And so if I just have a rose with a marking, we forget about the metric, right? That's what we do by contracting it to a point. So we forget about the metric. And then, so I just have a rose with a marking. How do I know whether 2 roses are connected by an edge or multiple roses are connected?
If they lie in the same joule. So.
Oh, that's just by definition. If I have some graph that has a marking which contracts to these markings on those roses.
Yep, that's it.
Thank you.
Yeah.
Good.
Any other questions or comments?
May I ask a general question, Peter? So there is this point of view that out of N can be thought of a mapping class group of connected sum of S1 cross S2s divided by some torsion and twists.
Sure.
Is there anything known about the mapping class group of other reducible 3-manifolds being virtual dual groups, or even cohomologically virtually finite?
This is not something I'm going to know the answer to. Someone else might.
All right, thanks.
Yeah, sorry.
I mean, there are these guys working on hyperbolic geometry and doing something in 3 dimensions. And what's his name? Iranian guy, should be Toronto now. Used to be a postdoc at UConn. I'll figure out the name, I can tell you. I think people are looking at that somehow. They have 3D pictures of outer space.
I see.
So I just point out that this
Kazarov.
Picture.
Sorry, the name is Kazarov.
The picture you described is useful in this next question about understanding the structure of the boundary of the dual complex. You can look at sphere systems inside connect sum of S1 cross S2s, and these are related to the sort of the components, the walls of the boundary. That's not your question. Just wanted to say it.
Oh, I have one more stupid question. Sorry if I'm holding everybody up, but so this simplicial complex LG that you construct, is that not homotopic to the boundary of the blow up or whatever? However, I forgot the names of the two guys that did it originally.
It's not. You're not going to see the boundary there. I mean,
or I guess you proving that something is that the simplicial complex is spherical, right? And the question I have is whether why this is not the same simplicial complex that probably showed up in these other guys' work that did blow ups instead of cutting off.
It's the same. Oh. Why is it not the same? No, that may be the same complex. The proof is different. The proof is using a combinatorial Morse function instead of the I guess they have an argument kind of with the actual Morse function.
Is it so it's I mean it's just homotopy equivalent, or is it do they literally think about the same simplicial complex as like isomorphic?
I'm not sure.
Simplicial complexes? Okay, thanks.
I haven't read those carefully. Yeah, but this complex L of G, right? You can see that there's a proper map from J of G to L of G, but you lose the boundary information.
Any other questions or comments? If not, I think we can thank Peter again.